All right, welcome back, everybody. Okay, so I really enjoyed the last lecture. I always like getting really good questions. This time I'm going to try to get through more than 2 pages of my lecture notes. So what I want to tell you today is kind of continuing this theme of analyzing ordinary differential equations. Okay, in the last few lectures, we've been looking at linear systems, x dot equals a matrix A times x. And we've been thinking about what the general solution of this would look like in terms of eigenvectors and eigenvalues of A. And we've characterized about half of the cases. Okay, so we're going to characterize the other half of the cases of 2 by 2 A matrices today. But before we do that, I want to tell you about nonlinear systems. So most of us in our research are not going to have linear differential equations, right? We're going to have nonlinear ODEs or PDEs for real physical systems. Okay, there's going to be nonlinear terms, all kinds of nasty stuff. But what I'm going to show you right now is how, under some pretty general conditions, we can approximate nonlinear systems by linear ODEs in a vicinity of fixed points where the dynamics equals 0. Okay, so how many of you have seen linearization of nonlinear dynamics before? How many of you have not? Okay, good. So we're starting to get into some new stuff. Okay, so we're going to linearize nonlinear dynamics. And we're going to do this near a fixed point. Okay, so let's say that in general I have some x dot equals some function of x. So instead of just a matrix A times x, this might be x squared or x cubed or x plus sine x, right? Something nasty. So in the homework, the pendulum example, you have something like, theta double dot equals minus g over L sine theta. So for any of you who didn't like doing all the partial derivatives, this is what you should get for the 5th problem on the homework. This is a nonlinear differential equation, right? Sine of theta is a nonlinear function. Okay, so for this, for now you can just think of x and f as being scalars, right? Just one value x, not a vector. But everything I'm going to write down is going to be completely general for vector x and a vector of functions f1, f2, f3, and so on. Okay, so I'm going to define a fixed point, x bar. This is a fixed point if f of x bar equals 0. Okay, this makes sense, right? The rate of change of my variable is equal to some function of my variable. If that function is equal to 0, then my rate of change of x is 0. My x bar stays put. It's a fixed point. Okay? Pretty simple. So x bar is a fixed point if the dynamics f, so I call f the dynamics. It's how my x changes in time. If that dynamics is 0 at x bar. Okay, so for x near x bar, so in some neighborhood of this fixed point x bar, so let's say that means that delta x equals x minus x bar is small. So for some small delta x neighborhood around my fixed point, I can write these dynamics as an approximately linear ODE. I can approximate the dynamics near my fixed point by a linear ODE. Okay, and I'm going to do that right now. So we're going to write down x dot, and x dot equals f of x. But what we're going to do is Taylor expand our dynamics, f of x, about the base point x bar. Okay? We're just going to Taylor expand. And this is in the 3rd lecture notes. So lecture 3, we have this exact formula I'm going to write down for this Taylor expansion of x about some other point x bar. So this is equal to f of x bar plus what? Plus the derivative of f with respect to x evaluated at what point? X bar. Okay, I'm going to write this derivative a little bit differently than I've written it before. I'm going to write big D of f with respect to x. This expression is going to be, this is just the derivative of f with respect to x. This is f prime. But this will also this is more general. If f is a vector of functions and x is a vector of values, this is going to be a matrix of partial derivatives. I'll show you what that is in a minute, but for now this is just the first derivative of f with respect to x, evaluated at x bar times my difference from x bar, x minus x bar, plus what's the next term? Okay, 1 over 2 factorial, second derivative d squared f dx squared evaluated at x bar times x minus x bar squared. This, again, just the second derivative of f with respect to x. I'm just using a new notation. Plus 1 over 3 factorial d cubed f dx cubed x minus x bar cubed plus dot, dot, dot. I just realized in my lecture notes I forgot the factorial. So remember, there's always factorials in these Taylor series. Okay, so what are some simplifications I can make to this expression right away if delta x is small? Yeah, so basically all of this stuff is small for delta x small, right? This is just delta x squared, delta x cubed. If delta x is like 0.01, this is 0.0001, and this is 0.000001. Real small, okay? What about this term, f of x bar? It's 0, right? This is my fixed point. So I can make a pretty decent approximation for small delta x that my dynamics near the fixed point is just this first derivative times delta x. Okay, so I'm going to write that down. So I'm going to write down a derivative in terms of this delta x variable. So x dot minus x bar dot. What's x bar dot? 0. It's a fixed point. It's not moving. So this is equal to d dt of delta x. Okay, so my delta x variable, my difference from my fixed point, its rate of change is just equal to x dot. And x dot is approximately equal to this term here. So it's approximately equal to df dx evaluated at my fixed point times delta x. Super important, okay? Okay, so questions about what we did here before I go on to do an example. Okay, we have a fixed point where our dynamics are 0. In a neighborhood of that fixed point, so where x minus x bar is small, so we're in a small neighborhood of x bar, then the first term in the Taylor series is 0. All of the higher order terms are nearly 0, and this is the dominant term in the Taylor series. And so I can say that the rate of change of my kind of distance from this fixed point is equal to this first derivative times that distance. Okay, it's a linear equation in delta x. If you want to think about it this way, you could say that we're kind of shifting our origin to the x bar fixed point, and this delta x is our new variable about that fixed point. So we're looking at the dynamics near this fixed point. Okay. Now what's kind of cool is that this expression is totally general. I can have this for a vector-valued function with a vector input x, and all of these terms still make sense. So I'm going to give you an example of what these look like for kind of a generic multivariable function. Okay. So let's do example. Okay, so if I have some vector function of some vector x, maybe this has, 2 components or something like that. I'm going to do this example where it's f1 of x1, x2, f2 of x1, x2. Okay. Now, the matrix derivative of f with respect to my vector x is equal to, how many of you know how to take this, this kind of big derivative, big capital D derivative? Okay, it's really straightforward and simple. Okay, so what we're going to do is we're going to get a matrix of partial derivatives. The first term is going to be the partial of f1 with respect to x1. Okay, I'm going to take the partial of my first row with respect to my x1. Then I'm going to take the partial of my first row with respect to my x2. Then take the partial of my second row with respect to x1, and the partial of my second row with respect to x2. This looks nasty, but it's actually pretty simple, right? These partial derivatives are usually easy to do, and I get this matrix of first derivatives in each of my variables, x1 and x2. If you ever want to remember what order like the f1s and the x1s go in, the way I think about this is I'm about to multiply this by a delta x, and so it's going to be like delta x1, delta x2. And so I better cancel out these delta x1s and delta x2s. And the first row is first derivatives of my first row. The second row are derivatives of my second row. That's how I remember where the f1s and f2s go. OK, good. So let's do a real example. So let's say that this thing equals x1 minus x1 squared and x1 plus x2. OK, so first things first, let's just take the big derivative, the first derivative of this function with respect to our variable x. OK, so df dx is going to equal, OK, what's the partial derivative of my first row with respect to x1? 1 minus 2x1. OK, what's the partial of my first row with respect to x2? 0. There's no x2s. OK, partial of my second row with respect to x1? Partial of my second row with respect to x2? 1. Okay, so this is my first derivative matrix. Okay, so going back to this equation here, we start to see that this first derivative is a matrix, which is good. So it's starting to look like x dot equals a times x. It's not exactly there yet, because this matrix is nasty, and it might have, like, you know, if this was an x1 cubed, then I would have had a 3x1 squared. It would have been nonlinear, right? The terms of this matrix could be nonlinear functions. That's fine. OK. So the general procedure to solve a system like this, I just made this one up in my office this morning, is we first look for the fixed points. We look for when this function is equal to 0. OK, so when does this function equal 0? OK, so just looking at the first row, when can that first row be 0? x1 equals 0 or x1 equals 1. OK, if x1 is 0, what does x2 have to be? 0. And if x1 is 1, what does x2 have to be? Negative 1. OK, so these are my two fixed points. These are my x bars, 0, 0, and 1, negative 1. So what we're going to do is look at this derivative matrix, and I'm going to evaluate it at my first fixed point, and I'll get one A matrix. And I'm going to evaluate it at my second fixed point, and I'll get another A matrix. So there are different linear dynamics around each of these two fixed points. Okay, OK, so let's think about it. So around x bar equals 0, 0, we have an equation ddt of, you know, delta x1, delta x2 equals this matrix derivative evaluated at my fixed point. It equals df dx at x bar times delta x1, delta x2. OK, so if I just plug in my fixed point 0, 0 into this matrix, what do I get? Right, well, I plug in a 0 for x1 and x2, and I get 1, 0, 1, 1. Okay, so what this says is that if we're in a near vicinity of the point 0, 0, this nonlinear nasty differential equation looks linear, and the linear dynamics around that fixed point are given by this A matrix times my delta x vector. Okay, questions about what we're doing here? Any questions at all? Okay, how many of you think this makes some sense? Okay, how many of you are a little lost right now? It's okay if you're a little lost right now. Okay, so luckily we have another fixed point, so we'll try this on the other fixed point and see if this makes more sense. Okay, so we do the exact same thing about our second fixed point. Right? We have these two fixed points, and we're going to look at what the dynamics look like in a small neighborhood around these two fixed points. So around our second fixed point, 1 minus 1, we get the same thing. We get ddt of delta x1, delta x2 equals some matrix times delta x1, delta x2. And I get this matrix by plugging my fixed point in to my first derivative of f. So if I plug in 1 for x1, I get minus 1, 0, 1, 1. Okay, good. This is called the Jacobian. df dx is called the Jacobian, or the first derivative. Okay, good. So I'm going to draw a little sketch now. So what does this look like? Remember, we like to think geometrically, because everyone likes pictures. x2, x1. Okay, so where are my two fixed points? One of them is at the origin, right? And the other one is at plus 1, minus 1. So I have a fixed point here and a fixed point here. I don't know what happens anywhere else, but I know that in some small region around this fixed point, the dynamics are going to look like this. And I know that in some small region around this fixed point, the dynamics are going to look like this. Okay? So so how do we solve a linear system? How do we tell what this linear system and this linear system are going to do? Yeah. We look at the eigenvalues and eigenvectors. Okay, so what are the eigenvalues of this matrix? It's really easy to find the eigenvalues of a lower or upper triangular matrix. Okay? Because if I take this matrix minus lambda I, and I take its determinant, I get a product of all of the diagonal elements minus 0. So I get lambda minus 1 times lambda minus 1 equals 0, and lambda equals 1. So lambda equals 1 are my eigenvalues for this. And for this one, lambda equals plus and minus 1. Okay, so what does it look like if lambda is plus and minus 1? A saddle point. Okay, so this fixed point here, I don't know what orientation the saddle point's going to be. I'd have to compute the eigenvectors to figure that out, but it's probably going to be some kind of a saddle point looking thing. And what does it look like if both of my eigenvalues are positive? It's just unstable source in all directions. So this is kind of, everything's moving away from this point. And this point, it's moving away in some directions, and it's moving in other directions. And I could figure out what the orientation of these directions are by looking at the eigenvectors of both of these matrices. Okay? So I don't know what happens between here. Probably something super interesting. Like I bet, well, it's hard to say. I don't know exactly what's going to happen here. There are other tools we're going to talk about later to figure out what happens in the middle and way out here. But at least I know that if I'm near one of these fixed points, I know what the dynamics look like. Okay? So this is similar for the pendulum. Okay, any questions about this example before I move on? Yeah? Okay.
Is that right?
Yeah.
What about like long-term like stability of linearization?
Okay, so the long-term stability of linearization is interesting. The idea, so this is a very good question, and it's something I wasn't sure if I was going to talk about because it's a little bit complicated, but it's really, really a good question. Okay, so I have a complex plane where all of my eigenvalues have to live. Right? All of my lambdas for any system I can ever write down are going to live in this complex plane. I might have plus and minus I might have plus and minus 1. I can have any eigenvalues, right? And let's say I have these 3 eigenvalues. So I don't know if any of you can't see, then it's probably on the board. But if I have these 3 eigenvalues, then anything in the left half plane with a negative real part is stable. So everything here is stable. Any eigenvalues on the right are unstable. And what we're going to do for the next example today is we're going to show that if I have eigenvalues exactly on the imaginary axis, then it's kind of neutrally stable. The fixed point doesn't, it's not a sink, not everything goes into the fixed point. It's not a source, not everything goes out. But things just kind of rotate around this fixed point forever, and they keep kind of the same radius. So it's neutrally stable. It's not really that stable. It's not unstable. Okay, so your question is what happens for long-time stability of these fixed points in a nonlinear system? Okay, so the way we can think about it, I wrote down my Taylor series expansion, and I kind of just brushed all of the higher order terms under the rug. But really, these are perturbing my linear dynamics. They're changing the shape near this fixed point of where the vector field, where all the arrows and all the vectors look. But if my delta x is small enough, super duper small, then I can bound a region around each of these eigenvalues where my new eigenvalues in this nonlinear system will be. Okay, so if I'm in a tiny enough neighborhood of this fixed point, my eigenvalues are going to be pretty darn close to 1, 1. And if I'm in a tiny enough neighborhood of this fixed point, my eigenvalues are going to be pretty close to plus or minus 1. So if I draw a really small kind of epsilon ball around the points that are stable here, if I draw the ball small enough, they're still stable. Even with the additional nonlinear terms, these are still stable forever. Same thing with my unstable points. Even if I add this nonlinearity, if I'm in a small enough region around this fixed point, it's still going to be unstable forever. Now, the points on the imaginary axis are the interesting ones, because my nonlinearity means I have this small ball of uncertainty around that eigenvalue, which means it could be a little bit in the positive half or a little bit in the negative half. So if I take a system that is a center, which is just kind of rotating around with these eigenvalues, and I add a nonlinearity, it could actually make it stable or make it unstable. So these are really dangerous points where if we write down the linear dynamics, we might think it's stable, but when we add even the tiniest nonlinearity, it can destabilize complex conjugate pairs of eigenvalues. So that's a great question because it segues directly into the next example, which is when I have complex conjugate pairs of eigenvalues. So thank you. Okay, so I wanted to show you how to linearize a system because this is on the homework. Okay, so you're going to have an equation like this. You're going to write down something like theta dot equals omega, omega dot equals minus g over L sine of theta, and then you're going to do something very similar to what we just did. You're going to find the fixed points, you're going to linearize about the fixed points, and you're going to assess the stability. Okay. Okay, I want to do one other example of linearization before I move on. And something to note, right, this Jacobian of f is a matrix. The second derivative is like, instead of a matrix, it's like a cube of values. I have to take f1 partial with respect to x1, 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 x2, x1, x3, x2, x1. Like there's this whole cube of partial derivatives here. This is like a 4-dimensional cube of partial derivatives. These things are called tensors. They're really nasty, and it's better to forget them for now. Okay? But it's kind of interesting to think about. Like, try to generalize what we did and imagine what the second Jacobian, like the second derivative of f with respect to x is. It's this really nasty tensor-looking thing. It doesn't look like a matrix, right? A matrix is a square of numbers. It's a cube of numbers. Okay, so the next example I want to do is pretty quick. And I just want to do another example of linearizing dynamics with a 1D example that's a little bit more straightforward. Okay. So we're going to do the logistic map. Okay, so x dot equals f of x equals x times some p max minus x. Super simple. Now this is really not a vector. This is just a number x. X is the population of some species. Let's call it humans. Okay, so this is my population. This is the max population that my planet can, that my habitat can hold. So this is the max population based on resources. There's only so much corn we can grow. Okay, and this is called the logistic equation. Interestingly, it's a super simple equation, right? It's like a quadratic nonlinearity. It's 1D. If I write down a numerical scheme to try to integrate this solution forward in time, for lots of numerical schemes, it's completely chaotic. And this actually suggests that if I have like population models where maybe people die at certain parts of the year or are born at certain parts of the year, or like rabbit populations, you can actually get chaotic limit cycles of like really, really large populations, then they crash, and then they go really, really big, and then they crash. So it's a really interesting equation. But for our purposes, it has two fixed points. So x bar equals 0, and x bar equals p max. Okay? I can linearize this about each of those fixed points. So I can say, well, df dx is equal to p max minus 2x, just the derivative, first derivative. And so we have kind of delta x dot equals p max minus 2x bar times delta x. This is my linearized equation, linearized about either of these two fixed points. This is exactly what we wrote down before. It's a 1D example. Okay, so let's just plug in the two cases. So case 1 is x bar equals 0. So what does this equal when x bar is 0? P max. It's a big positive number, right? Maybe we can hold 10 billion people. So then df dx equals p max. This is my eigenvalue, if you will. And it's positive, so it's unstable. Okay? Case 2 is x bar equals p max. So now I plug that in here, and I get my eigenvalue is minus p max. Right, I just plug in my fixed point, and I get p max minus 2p max. It's minus p max. So it's a minus big number. So it's really, really stable at this case. So I can draw the phase portraits, or the xt diagram, if you want, for this system. Okay, so this is my population x in time. I have two fixed points. I have 0 population and p max. These are my two fixed points. Okay, so which one of these is stable and which one is unstable? 0 is unstable and p max is stable. This makes sense. 0 is unstable. If I have like 2 people, it's going to exponentially grow until I saturate and hit my max population, or at least with bunnies. And p max is stable. If I have a too few people, it'll kind of, the population will increase. And if I have too many people, those people will die until it goes into equilibrium. So the equation looks essentially like this in time, kind of exponential attraction onto Pmax and exponential repulsion from 0. If I ever had negative people, I would get negative a bunch of more people soon, which is bad. So this is a really simple example. We can draw it, like we can interpret what the solution means, right? This is like if you started with a small population of people on an island, it would blow up until it hits the carrying capacity of that island, and then it would saturate. And if for some reason you dropped 2,000 more people, 2,000 more people would have to die. Okay? Okay, so it's a simple example. Okay, so we know how to linearize systems, and so this is giving us a whole kind of renewed interest in looking at x dot equals ax, because we can actually do something useful with it. Okay? So if we have some interesting nonlinear system, we can linearize it around fixed points, and we can look at what those fixed points do locally, and we can start getting an idea of what even the global dynamics of my nonlinear differential equation will look like. And this is actually what people do to plan spacecraft missions and trajectories in complex chaotic systems. So for those of you who are interested in control, there might be some fixed points that are unstable, but they're really good fixed points that I want to be around. Like, for example, if I have a flat plate with fluid flow going past it, then I have some boundary layer. And at some point, I get a transition into a turbulent boundary layer, and my drag explodes. And what I might want to do is try to stabilize this unstable laminar boundary layer. Right? If we could get laminar flow over all of our wings and trains and cars and everything, then we would spend $50 billion less a year in gas. So we want to stabilize laminar fluid flows. This happens to be an unstable fixed point in a very high-dimensional differential equation that's nonlinear. So in the very, very high-dimensional differential equation, x dot equals f of x, where this is the Navier-Stokes equation, and my x vector is my vorticity or velocity at every single point in the flow, billion-tall vector, laminar flow is an unstable fixed point. And with feedback control, I can actually stabilize it, and I can maintain laminar flow even though I have these nonlinear dynamics, because I'm in a vicinity of that fixed point. So this is just an example of what we might want to do with stabilizing nonlinear systems or analyzing them. Okay, so the example that I'm going to do now, how many of you are interested in fluid flows? Okay, a few of you. I'm very interested in fluid flows. We're actually close to being able to do this on real wings and trains and planes and cars. And I would say in the next 50 years, we're going to have active control to stabilize unstable fixed points in fluid systems. Like, it's going to happen. It's going to be awesome. It's going to save the world a lot of fuel. Okay, so we have some system dx dt equals ax times ax. Okay. So this is a case that we haven't covered yet. We started hinting at it. But if we look at the eigenvalues of this A matrix, so if we look at the eigs of A, we find that they're plus and minus 2i. Okay? That's a little bit strange, because this is a real valued matrix. This has real valued solutions, but it has complex conjugate pair of eigenvalues. So these are on the imaginary axis of the complex plane. Strange. Okay, so how do I solve this system once I know the eigenvalues? What's the next step if I want to know what the full solution is? I need to know the eigenvectors. Okay, so we're going to do C1 for lambda 1 equals 2i. Okay, so I have A minus 2i times C1 equals 0. And A minus 2 times, it's A minus lambda I. So it's 2 times an imaginary number times the identity matrix. Wish there was a different letter. Minus 2i to minus 2 minus 2i times C1 just call this x and y equals 0, 0. Okay, so what has to be true for this vector to multiply my a minus 2 lambda I and get zeros? Okay, so try x equals 1, and then we have that y has to equal I. So you can kind of plug this in and verify that this really is an eigenvector. So 1 and I is my C1. Okay, let's try C2 for minus 2I. A minus is a plus 2I times the identity. C2 has to equal 0. So now we have 2I to minus 2I times xy equals 0, 0. Again, I'm going to assume that x is 1. And if I plug in x is 1, then y has to equal minus I now. Okay, this is weird. My eigenvectors are complex. But I can still write down the full solution. I can write down x at time t equals my matrix of eigenvectors times e to the diagonal matrix times t inverse. And what we're going to find is that when we stack these eigenvectors into t and we write down this expression, all of the complex numbers are going to cancel out, which is good. So you can take my word that t inverse equals 1/2 times 1, 1 minus I. Okay, I know this is boring. This is the second time I've done this. This is only the first time you guys have done this this week. So the point, though, is that something magical happens when you actually write this down, and I want us to actually see it to believe it. I think it's really very important that when you actually write down the solution, all the imaginary parts cancel and you get real numbers out. Okay, so we're going to say x at time t equals big T e to the diagonal t, t inverse, times x at time 0. And I'm just going to start writing this out. So I'm going to pull my 1/2 from my t inverse out front. So this is 1/2 times, okay, my matrix of eigenvectors is 1I, 1 minus I. E to the diagonal t is e to the 2it, e to the minus 2it. And t inverse is, I already pulled out the 1/2, and now I have 1, 1 minus I. Okay, and this is, of course, times x naught. Okay, so now we're just going to multiply these two matrices. We're going to get, okay, we still have 1/2, 1I minus I1 times, and I have e to the 2it, and then I have e to the minus 2it, and then again I have minus I e to the 2it, and I have I e to the minus 2it. This is kind of a mess. You have to be very careful to get everything right. And finally, when I multiply this out, I get, this is times x naught. I get 1/2 e to the 2it plus e to the minus 2it. And then I get I times e to the 2it minus e to the minus 2it. Right, this times that. Okay, then I get I times minus e to the 2it plus e to the minus 2it. And finally, if I didn't mess something up, I get e to the 2it plus e to the minus 2it. Okay, this is not as bad as it looks, right? It's not great, but it's not as bad as it looks. You can do all this multiplication. Yeah, there's complex numbers. We know what I times I is. This is the full solution. Okay, but we still have e to the 2its and e to the minus 2its, and that's not great. So how can I simplify this kind of to the final level? What's the final level of simplification for this? Right, I can use that formula that we derived in like the second lecture for e to the ix. Right, so we have this Euler's formula. E to the I theta equals cos theta plus I sine theta. And let's just write down what e to the minus I theta is. So if I plugged in a minus theta here, what's cos of minus theta? Just cos theta. And what's sine of minus theta? Minus sine theta. So this is kind of good, right? We have kind of the same real part, but we have equal and opposite imaginary parts. So this is starting to look like these might be able to cancel if we added these together. Okay, and that's exactly what we're doing here. So we have e to the 2it plus e to the minus 2it. That's cos 2t plus I sine 2t plus cos 2t minus sine I 2t. And so that's just 2 cosines of 2t. Perfect. This term canceled out to something real. And this is the same term right here. So the second diagonal is also going to be 2 cosine of 2t. Okay, what about this term here? What's minus e to the 2it plus e to the minus 2it? So minus this guy plus this guy is minus 2I sine 2t. So minus 2I sine 2t. But remember, we have an I out front that we're multiplying it. So it's minus 2I squared. What's minus I squared? Plus 1. I squared is minus 1 minus that. So this is plus 2 sine 2t. And if you do the same thing down here, you find out that you get a minus sine 2t, minus 2 sine 2t. And my 1/2 cancels everything out. But the bottom line is my solution for, let's write this as a vector, x naught and v naught. My solution to this differential equation, right, it had complex eigenvalues, plus and minus 2i. But the solution for any real valued initial position and any real valued initial velocity are real, right? They're just sines and cosines of my position and velocity. And in fact, we find that my position and my velocity are out of phase by pi over 2, or 90 degrees. Okay, so in the example we did earlier where we took the spring mass system, right, with no damping, we had a complex conjugate pair of eigenvalues, plus and minus I omega. And when we pulled this mass back and let it go, it just oscillated forever. And remember, as the position is oscillating back and forth like a cosine, the velocity is oscillating back and forth like a sine. So it's out of phase. And that's exactly what we see here. If we just start with some x naught and v naught is 0, we have our final position is cos, and our final velocity is minus sine. So they're out of phase with each other. And that's a really nice interpretation for what it means when we have complex eigenvalues. Okay, so we can have complex eigenvalues in a system that's real valued, and that means that some of my states are out of phase with each other. They're doing cosines and sines out of phase with each other. That's exactly what my position and velocity are doing. Okay, so for the last thing, I'm just going to draw the phase portrait because it's nice to see what this looks like. And we're going to use it next time. Okay. This matrix also, for those of you who recognize it, this is a rotation matrix. This takes my initial x naught and v naught and it rotates it by 2t. So as time progresses, my initial vector of position and velocity is just rotating, but its radius is not changing. I mean, you can try a vector, like plug in a vector x naught, v naught, multiply it by this matrix, and you'll see that it rotates that vector. So if this is x and v, and this is my, x naught, v naught, my solution just stays on these circles forever, these concentric circles. Okay, so that's what the phase portrait looks like for this system with complex conjugate pairs of eigenvalues. And it's called a center because it looks like a bullseye. So I guess the point here is we can do all of this math with complex numbers. It doesn't matter at all. You can have complex valued lambdas, complex valued eigenvectors, and you can still get solutions using the formula that we derived before this formula. And these systems are neutrally stable. If I add the tiniest bit of damping to this equation, so I have a little -1 or -0.1 here, then my center becomes a spiral sink. You'll find that my eigenvalues will look like, minus something plus or minus 2i, something like that. So it'll be stable and oscillatory. If I add a little negative damping, so this thing is kind of going unstable, then I'll get a unstable spiral. It'll kind of blow up and oscillate as it does it, kind of oscillate in sines and cosines. And so this gets back to Ben's question of what happens when I have a nonlinearity. Well, these eigenvalues could go a little bit unstable or a little bit stable. And that's a tricky thing to analyze. It's actually pretty complicated. So what it means to have like a negative real part and an oscillation means that I have this exponentially decaying envelope, e to the minus t, and my solution is oscillating as it's decaying. Right? If I plotted x with respect to time, that's exactly what it would look like, is this decaying oscillation. Okay, so I want you to play around with these things. Okay, this is not a whole class in dynamical systems. I can't we could spend a whole week looking at these types of systems. It's very, very interesting. Try some of these out, plot them in MATLAB, play around with adding damping and see what the eigenvalues do, see what the phase portraits do, and convince yourself that this is really what's happening. I mean, in MATLAB, you can literally do this ODE 45 simulation and then plot the x column of the output against the v column of the output, and you'll get this phase portrait. Okay, so in the next class, what we're going to do is combine all of these ideas. We're going to take nonlinear systems from physics, from F equals ma. We're going to identify the fixed points, and we're going to use these linearizations to start getting a global view of what the dynamics of systems look like for nonlinear systems. Extremely useful. This will allow us to figure out where spacecraft and asteroids go, among many, many, many other things. Okay, that's all for today. I'll see you on Friday. Thank you.